It's my honor to talk here. Okay, today's the title is Names and Numbers Organizations. Okay, actually this is some kind of narrow sense of the internet governance because that's related to how internet works and how to policy those kind of. Okay. So back to the first one. You want control? Okay, next one. Oh, okay, as I mentioned, that's the narrow size, so next, please. Okay, we will talk about parameters because in order to make network running, we need some unique things or identifiers. And so that's the thing. And then after that, that's the internet and the numbers. And as Professor Chang mentioned, we need to address technical things. What's this idea of switching, layering, and the numbers and the operations? That's the examples. Then we will discuss how those kind of numbers assigned or allocated to the internet operators on even the national internet registries and the trend. So next slide, please. So actually there are two kinds of, we are talking about science, we are talking about engineering. So the first one, this one is the science, the natural parameters. Usually actually we talk about the locations, so, and then we talk about the time. And in the communication or networking, we talk about spectrum or those kind of things. So that's the three fundamental things. Actually, not really three, because if you're familiar with the physics or remember, they are the uncertainty principle. So actually, time and the spectrum are related. You cannot get both accurate. So next one. Then we talk about engineering. So there are a lot of human-defined parameters instead of like the location, the time, frequency. And so those are the examples in the internet area, and that's related to the governance. The first example is the telephone numbers, right? We all know the telephone numbers. The policy was defined by International Telecommunication Unit. That's under United Nations. That's very government-oriented organizations. That's the old days for the telcos. Then actually we have the phones, mobile phones, we have the computers, they are the Ethernet. Ethernet is the universal thing. And each Ethernet interface has its unique address, which is called the MAC address. And that defined by the industrial organizations, that's IEEE, okay, mainly in the United States, but now it's international. And then internet come out. There are several things related to internet for the parameters. Okay, there are the autonomous system numbers. Okay, that's probably the ordinary users don't know, but if you are network operator, that's very important. The related thing is called the BGP, Border Gateway Protocol, because internet by definition is not centralized. It's distributed, and each network connected and peering with each other using the protocol of BGP. And how to define the different networks, that's the autonomous system numbers. Then IP address. We have two types of IP address. One is IPv4, that's, for example, 192.186.2.3, that's IPv4, separated by stops. And for IPv6, because luck ran out of the IPv4 address, that's only 4 billion addresses in the theory. So actually, also in reality, so, and the total number of the population is more than 7 billion. So we do not have enough IPv4 address for everybody. And so that's the IPv6 address. That's plenty of address space. And the funny thing defined is they use columns to separate. So that's 2001 column DB8 column whatever. You may wondering why the English characters show in the address, because that's the hexamal. So that's 3 numbers defined using 0 to 9, A, B, C, D, E, F. So that's why you don't need, please do not expect it to some letters bigger than 5. Okay, then we discuss some, okay, so atomic numbers and address, whatever V4 and V6 are defined by IANA. That's the Internet Authority for Numbers and Address, and also with the regional internet addresses, registrations. So that's the thing, the policy or governance thing. And then actually we talk about the transport layer. That's TCP or UDP. So there are more than TCP and UDP. In total, there are 256 different transport layer protocols, but ordinarily we use TCP and UDP. If you know how to do ping, then that's another protocol number. Then above that, that's the port numbers. So TCP, there are 16 bits define different port numbers, and the most useful one are port, for example, 80, that's HTTP, World Wide Web. And currently, because encryption or those kind of things, we have a very strange number called 443, that's HTTPS. So basically, there are 2 important numbers for TCP, most important numbers. And for UDP, actually, the domain names lookup, it's based on UDP protocol, and the defined well-known number is 53. Okay, then there are domain names because the numbers are not easy to remember, so we use domain names. So that's the thing. And also the port numbers and the protocol numbers are defined by IETF, Internet Engineering Task Force. And the domain names, that's the TDLD, CCTLD, all those kind of things. So next slide, please. So Internet Assigned Number Authority, that's IANA. Originally formed by John Pastel. He was passed away. He wrote a lot of RFCs. And there are 3 things related to IANA. That's domain names, that's number resource, and the protocol assignment. The domain names, as I mentioned earlier, that's the names, right? And the numbers, that's the atomic number, that's the IPv4 address and the IPv6 addresses. And the protocol assignments, that's the protocol numbers and the port numbers. Next slide, please. So then we discuss the switching technology. In the old days, in the ITU days, that's circuit switching as the telephone network. And the later internet, that's packet switching. For circuit switching, each pair of the communication allocate a circuit or virtual circuit, and the people occupy this circuit during the session. However, the packet switching is statistically shared. And then there are the virtual circuit switching and the datagrams. For internet, that's datagrams. And the keyword for virtual circuit and the datagram, one is called connection oriented. So as I mentioned earlier, for session, there's a circuit. However, internet is connectionless. So whatever the way to send the packet or message, there is no virtual circuit. So it's very flexible and reliable method. So the first question in this talk is, why are the global unique number required? So I believe the answer is clear. We can discuss later. Whatever thing we need to have some kind of numbers to identify the endpoints in the communication process. Next slide, please. Then the most important thing is the layered structure, because network is defined by, invented by the engineers, by the human, and we are not the God. So we are not perfect. We cannot really understand everything. So the key word for big project or big engineering to success is decomposition. And the way people to do is vertically decomposition and the horizontally decomposition. And the layered structure is vertical decomposition. They are the physical layers that's dealing with the natural parameters like time, frequency. Then we digitalize that. So that's the digital world. For the IEEE, we call it the link layer. That's the MAC address to identify. And then the global thing is the IP address, whatever V4 and V6. That's called the network layer. Then, because, as I mentioned earlier, network layer is datagram, is connectionless, it's not reliable. So we need another layer to make reliable end-to-end communication. That's transport layer, like TCP. So they are the port numbers. Then to the application layer, we need domain names to either remember or even the URLs. Next slide, please. So again, addressing are different for different layers. Like a MAC address for a link layer, that's 48 bits defined by IEEE. IP address, IPv4 32 bits, and IPv6 128 bits defined by IANA. And the port numbers, 16 bits IANA. And the domain names, ICANN. And the URL, that's text. So that's the thing. And the one thing is important because there are different layers, so we need mapping schemes. The MAC address to IP address mapping. And the combination of the transport TCP UDP numbers with IP address, we call 5 tuple. And the names and the IP address as the domain name system is doing. Next slide, please. So, okay, I believe I can make very quick, right? IPv4 address, the format, and the IPv6. And the one thing for IPv6 is there is a short form, so you can skip the zeros and the column imply in between they are all zeros. Next slide, please. So for operation, we discussed the different layers and how internet operates. Actually, there are 3 levels of operation. Basically, the internet equipment is for forwarding packet from the source to destinations. So the subnet level, actually that's the mapping between MAC address and the IP address. And the intradomain, that means you on your own network, that's basically only related to IP address, whatever IPv4 or IPv6. And there are interdomain routings, so that's related to IP address and autonomous numbers and those kind of mapping through BGP, through something called ARP. So that's the way it operates. Next slide, please. So I also mentioned earlier, there is no centralized control for the operation of the internet. So each network for interdomain routing is pairing with a protocol called the BGP, Porter Gateway Protocol. So how big of those kind of pairing? And this can give you some numbers. For IPv4, it's starting from 1987. That's this figure draws. And Jeff Houston actually still keep this graph. And you can see that's from the total IP prefix, IPv4 prefix announced, you can see in the global routing table. And that's the total number of atomic systems you can see in the global routing table. And in IPv4, it's about 10 to 1. So each network announces about 10 prefixes. You can see the increase of this. And there are some interesting things inside. For example, you can see there is an increase, and then flat, then increase again. Guess what are those kind of difference or change? Okay, that's internet originally that's as linear increasing, then get exponential increasing. That's actually about the year 2000. That's the internet bubble. Then the bubble disappeared. You can see the flat of the routing table, then pick up again. So you can see a lot of interesting story, even take a look of the global routing table. And the atomic system numbers, that's the number of networks, it's still increasing. And for IPv6, currently the IPv6, it's about 1 prefix per atomic system, but it's also increasing, so this is good. We can see the internet still increasing, whatever no matter it's v4 or v6. Next slide, please. And for IP address, actually in the engineering domain, people discuss the IP address is in trouble. Why? Because something called overload. And because the address play 2 roles in the internet operation. One is we call locator, because that means where you send your packet to. Another is the identifier, which actually define the sessions. That's the 5 tuples. So that means you need the protocol, and you need the source address, the source port, TCP or UDP, a destination address and the destination port. No matter it's v4 or v6, that's the 5 tuples. That's the important thing. So IP address both serves as the locator and the identifier. And the people discuss if we can separate that. If we can separate that, will be create a new word. Next slide, please. And one thing actually is related is because run out of IPv4 address, so people talk about how about use some private address and map, communicate each other inside the enterprise network. And if those computers want to talk to the outside world, that's the internet, then help the map the private address to public address. So that's something called NAT44. So you can map private address to public address. There are 2 benefits for the NAT. The first thing is better security. Okay. Like because people outside, if you do not initiate communication, then people cannot go get you from outside. And another thing is more important actually is the saving of the public IP addresses, because I mentioned port numbers, they are 65 16 bits port numbers. So if you have a NAT device, then several internal hosts can share a single IPv4 public address to communicate with the internet. And the current ratio, like probably 100 people share a public IP address. That's average. And the extreme case, it's more than 1,000. So you can see that actually creates a lot of problem for security when you do traceback in the current internet. Next slide, please. Another thing, actually, that's my area. Okay, I mentioned the IPv4 address is not enough, so people run IP or start IPv6 project. However, IPv6 and IPv4 are not compatible. That's a big problem. If, like the telephone numbers, we know originally the telephone numbers are short, and later actually the telcos extend the telephone numbers. Then you can use whatever the short or long numbers you can talk. However, when IPv6 designed, it's not smart. So v4 and v6 are not compatible. That's create a big problem. And the old proposal for V4 and V6 transition is for the new computers, you run dual stack. That means the new computer, you have V4 and you have V6. If the other side is IPv6, then you use IPv6 to talk. If the other side is V4, then you use IPv4 to talk. So that's the idea of dual stack. However, in reality, it's quite strange. Imagine if everybody else are dual stack, then you do not need dual stack. You can only run V4. If everybody is thinking this way, so selfish, right? Nobody will deploy IPv6. That's why the transition from V4 to V6 is always delayed. And what our research group is doing is, how about build a NAT, but that's a NAT 6.4, and translate between V4 and V6, not only the numbers, address, but also the protocols. It's possible. So we developed a NAT 64, and that means we can talk. And because V4 and V6 are not compatible, so in reality, actually, a real IPv6 host talk to an IPv4 host. The real IPv4 host, V6 host, think the other side is V6, but that's a mirror or image of the real IPv4 host. So that's the way translation works. And the tough part is use IPv6 represent V4 is very simple because there are a big amount of IPv6 address. So whatever a subnet in IPv6, that's usually 64 bits, can contain the whole global IPv4 internet. But how to use IPv4 to represent IPv6 is a challenge. And our method is quite simple. Like we choose a subset of the IPv6 address, which has the mapping relationship or algorithm-based mapping relationship between V4 and V6. Then we can use this part of the V6 address first. And later, if more and more people talk to IPv6, then we use the rest of the IPv6 addresses. So that's the mapping. The keyword for this is, okay, mapping is possible and important. The second, it's better to based on algorithms, not the dynamic routing or mapping table. I will talk to that later. Next slide, please. Another thing is interesting, that's also for our network's contribution, is called SAVA, Source Address Validation. Okay, originally IP address or internet's end-to-end, so whatever people use the public IPv4 address, you can trace back to the origin of the sender. However, later, as the introduce of the NAT 4.4, and several hosts share a single IPv4 address, then actually you cannot really trust this public IPv4 address. However, in the IPv6 world, because there are plenty of IPv6 address, so we can restore the end-to-end principle. Then probably for routing, we can also check the source address. That will make IPv6 internet more secure. So that's the idea proposed by my colleague, Professor Jianping Wu. The next slide, please. And how those kind of numbers important for operation of the internet. So let's make prediction. This actually is the prediction by National Science Foundation in the United States. The numbers are quite interesting. In 1980s, the year 2016, and the prediction of 2051. And the interesting thing is this. Okay, in 80s, it's about 10 people share a computer. And in year 2010, actually, one people has like 10 hosts or 10 address. And NSF predict in the year 2050, each person will have 1,000 devices connected. So that's the thing we need to govern this, right? That's a big governance challenge, yeah. Okay, so next slide, please. Okay, and the interesting from engineering or science is any problem in computer science can be solved with another layer of indirection. So that's the computer CS. So let's review what we talked. The IEEE MAC address link layer to IP address, that's the protocol is a method is called ARP in IPv4 and the ND neighbor discovery in IPv6. And the private IPv4 address to public v4 address, that's NAT44. And the IPv4 address and the IPv6 address mapping is NAT64. And the domain names and the address mapping is DNS. And actually, about 10 years ago, there is something called the enum is quite hot. That's mapping using domain name system, the telephone numbers to IP address. So those kind of things. And for the governance, because involving of the technology, we will see there are more mapping things come out, and the governance should adjust to allow those kind of new mapping come out, right? If the regulation is too strict, then probably they will stop or slow down the technology development, because the key idea in CS is add another layer of indirection, whatever thing. Next slide, please. Okay, for the governance. So they are the address. So we talk about the numbers or the names. And so one thing very important is make the uniqueness of those kind of numbers. Imagine if one entity in China and another entity in the United States use the same address, then that will introduce trouble, because ambiguity, you don't know how to send either the entity in China or entity in the States. So make the uniqueness of the numbers is very important. And how to make a uniqueness, that's the governance taking place. So that's the ICANN. Originally, actually, all those kind of allocation are by the United States. Then actually the US government tried to set up international organizations. So that's the ICANN. And under ICANN, actually, it's the names supporting organization or address supporting organizations. So next slide, please. So the structure, okay, the ICANN for address. So ICANN has a board of address supporting organization. And then the regional internet registries, for example, in Asia Pacific, it's APNIC, North America is ARIN, in Europe it's RIPE-NCC, and the LACNIT in Latin America, and AFRINIC in Africa. Then those kind of regional registries elect NCs, and that form the NRO, Number Address Organization. So that's the thing, and they are executive councils, and they interact with the ASO under ICANN, so to make the number policies. Next slide, please. So the process as similar to previous. So the policy making process is regional community. Under each regional registries, discuss the regional policy, then form the NRO to submit or whatever, discuss, interact those kind of process to ASO, then as ICANN, then finalize the policy, then the feedback to the regional registries. I somehow also familiar with this process, at least in the early days, because I was served in APNIC Executive Council for more than 8 years. So that's things. So the policy development. It's quite interesting. For example, the IPv4 address allocation, originally you can get a 4 Class C address. And then later, because run out of the global pool, that's shrink. So that's the thing. Next slide, please. So that's the regional internet registries for numbers assignment. Next slide, please. And the policy, okay. That's, so the policy related are 3 considerations. Okay, the first, the most important is make sure the IP address, public IP address are unique. And the second, the internet operation, that means we need to reduce the routing tables. You can remember there is a curve of the increase of the global routing table. It's somehow exponential. That gave a bad impact for the operation of the internet because the memory, CPU process this kind of big number as a tough thing. So when you allocate IP address, you need to make it aggregate. So it's only one entry can suit your requirements, not multiple entries. If multiple entries, that increase the global routing table. However, the saving make higher efficiency of the IP address utilization and the routing aggregation are opposite directions. So you need to make trade-off and balances. That's why we need governance and policy. And the trust, that's the identification, also make the uniqueness. So we can compare this with others, right? So that's the way policy debate or whatever. Okay. And so I mentioned earlier, right? The objective conservation, efficient use of the resources. And that's based on demonstrated need. Okay, that's my experience. Like China is big. In the early 90s, we tried to build a CERNET and also community internet. So originally we are thinking, well, we should talk to internet registry. That's Internic, because there's no APNIC. And we told them, okay, this is the population of China. We need a lot of IP address, but that policy way doesn't work. The policy is demonstrated need. So we need to tell them how to build the network in the first stage, then later how to do that. If convinced, then we can get the IPv4 address, and later we tell them, okay, it's expansion, we do not need enough, we do not have enough, so that's the way. And the aggregation I mentioned earlier, limit routing table growth. And the registration, that's uniqueness. Next slide, please. And how to make the demonstration of the requirements, you need to work on technical details. So that's the network plan. The routers, the servers, all those kind of things. Next slide, please. Then you work out the network plan. So what's the address you want, because you don't know exactly, so that's zeros. Then the sub-network masks, and the total, the current requirements, 6 years requirements and 1 year's requirements, and tell regional registry how to use that. So that's detailed, efficient, and accurate. And the one thing actually confused, how to prove that you really show you have this kind of requirements, right? So actually you just gave a detailed design for that. And the people talk about why not ping the IP address, right? Some people talk, okay, you can ping if that's alive. But regional registry does not trust this kind of method because you can program, right? For a single host, you can respond for 10,000 of IP requests, so it doesn't work, right? So, and another thing, operation, this is an interesting example, like how the trust is important because IP address announced by BGP protocol. Then how to make sure that's the right announcement because the IP address can be hijacked, okay. So this is an example, like ISP try to make the blacklist, like China is making the Great Firewall. One of the way to deploy Great Firewall is try to announce somebody else's address, for example, YouTube, right? The China block YouTube. So you announce that, then the people visit YouTube will go to your black hole and it cannot work. However, if you have to be very careful to limit those kind of announcements inside your network, if you're not careful, then actually that leak to the global internet. This is a real example in the year 2008. And the next slide, please. That stopped global user to visit to YouTube for 2 hours. So you can play tricks to do that. So actually, internet operation is somehow, security is important. So if you are not careful, then in trouble. Next slide, please. And the one way is called the resource public key infrastructure. So each address is signed by some kind of signature, then make sure. But that's controversial. Next slide, please. So the trust. In the old days, circuit switching, because the telcos allocate circuits for you, so you can trust the telcos. Next slide, please. However, for internet, originally people talk about end-to-end address. That's important, good. However, because of NAT, next slide, please. So actually, so that's the original one. Next slide, please. CDN, content deliverable system. So actually, if you visit Google, and in Thailand and the States, you can see different address. So that's the load balancing. The domain name is trustable, but not the IP address. Next slide, please. Because of the NAT, so actually, many people share a single IPv4 address, so not trustable. Next slide, please. And IPv6 transition makes this trust thing not trustable. And my argument is for NAT64 stateless based on algorithm. That's good. Okay, a little bit expansion. Okay, I strongly believe stateless in engineering terms. That means algorithms. So everything is algorithms. That's good. And we talk about artificial intelligence. How to trust artificial intelligence if the algorithm is public available. That's important, right? And I'm not a lawyer, right? But I believe the laws, that's because the law itself is some kind of algorithm. If that's public available and no ambiguity, then it can be trusted. Next slide, please. So the new internet playground, that's quite interesting. The platform hides users' activity, application hide itself, and the domain names try to, outplay interesting things. And I believe that may result in the fragmentation of the internet. Internet governance, the first job is try to avoid the fragmentation of the internet because we need a global internet. Next slide, please. Okay, so comparison of that. Next slide, please. So the naming. Actually, naming, as I mentioned earlier, we can trust the names rather than address. But currently, like actually Facebook, like Twitter, they do not really rely on domain names. The enterprise maintain their own database, so that makes things not good. Next slide, please. And the domain names, whatever, that's from the single host file to the domain name system and the Ncast and the IPv6 make the domain names interesting, and the DNSSEC, that's another certificate and a transition, so that's the thing. Next slide, please. Okay, the telephone numbers is old model. Next slide, please. So there are some things, numbers versus domain names versus IP address for the trust thing, who man operation that, so that's the policy. Next slide, please. So URLs provided by your own self, URL provided by provider, and the telephone numbers and the service specific thing like I mentioned Facebook or those kind of things. So finally, okay, for numbers like IP address, we need a uniqueness, operation, trustable, and some kind of governance scheme. And the names also those kind of four things. And in the old days, telcos case as multilateral under United Nations. And the current internet model for governance, that's multi-stakeholder. However, for the trustness, probably we need to have some kind of roots or trust anchors. That's the problem. And as people talk about blockchains, that is fully distributed. So can we rely on blockchains to do address allocation to make the uniqueness? Can we use blockchain to do domain name mapping? Or can we use blockchain or distributed scheme to limit the power for the Facebook, Twitter, or Google, or WeChat, all those kind of big giants? That's our job. So what's are the future directions? I don't know. Thank you very much.
Thank you. Very comprehensive presentation. But when hearing your presentation, in the IPv6, there are lots of facilities, liabilities, AG, security, lots of things. Why this IPv6 going to be a problem in implication of our migration to IPv4 to v6 in developing countries? Why, like China, the developed country, Chinese Communist Party pushed for IPv6 adaptation? What that type of problem raised in the migration of IPv4 to IPv6? My question is, what are the challenges, what are the problem migration from IPv4 to IPv6?
You mean the why?
Why?
To
Why need the Chinese government, Chinese Communist Party forced to...
the Chinese government? You mean,
not only Chinese government, all over the countries.
Oh, okay. Yeah, I believe for V4 to V6 transition, okay, there are several things. One thing is actually the government want the traceback. That's important. And the net for 4, like the net in V4, the traceback is not good. So that's one thing. Another thing, as I mentioned earlier, the IoT, Internet of Things. For Internet of Things, actually, you need end-to-end addressable. And the net, actually, it's good for clients because you want to call out. However, for Internet of Things, that's the sensors. You want, so sensors, in my theory, that's the servers, not the clients. Because you want to find, for example, a sensor is smoke detector. If it's a client, then probably every 5 minutes, the sensor will report the information. However, if something in the between, then probably you are in trouble, right? And if the sensor is a server, then whatever, you can monitor this kind of thing every time, every second. So that's why the new applications need IPv6. So that's basically 2 factors. The traceback for national security and for IoT. And for China, actually, it's interesting, right? China started IPv6 quite early, but because there is something called IPsec in IPv6, and that scared the Chinese government because they cannot monitor or build a great firewall for IPv6. And later, they found IPv6, IPsec is mandatory for the equipment, not for operations. So actually, people not really use IPsec. So that makes sense. Another thing that's quite interesting, like I like to thank especially Indian people, right? Okay, the Chinese government has an idea of if the United States in advance, no problem. However, they suddenly found the IPv6 population in India is very high. So that really scared them. They want IPv6. That's a true story, but nobody really talked in the news. Okay,
thank you.
So that's good, right? Yeah.
Many thanks for your lecture. Part of your lecture remind me one of the ICANN meetings, I think March 2014. It was a long discussions and debate regarding Guyana transition.
Mm-hmm.
My question is, what do you think of Guyana transition? Are really Guyana transitioned a part of their functions to the global multi-stakeholders community?
Mm-hmm.
Thank you.
Mm-hmm. Okay, thank you. Personally, I was in the Internet Architecture architecture board, IAB member during that transition. Personally, I think that's in the right direction. Maybe some details not need to be finalized or make it better, but basically that's a good thing.
Okay, thank you.
Hello, Professor. I'm Michael from Indonesia, Michael Takuchi. Actually, I work in international provider, so I really understand your lecture because it's technically. My problem when I work in ISP as a network analyst, sometimes I'm also using the net flow. So I need to analyze the traffic. And my problem is when the network is behind the NAT, I cannot trace back.
Yeah, yes.
So I cannot find who is the bad guy. That is my problem. And then, what do you think about the bad guy was using another country proxy to mask their IP address? I think just that my question. Thank you.
Yeah, that's very important thing, like because of net. That's why, back to my earlier answer, we need IPv6. So actually, in theory, there is no net in IPv6, so you can restore the end-to-end transparency. And in China, actually, the Chinese government require ISP to keep net logs for at least 3 months. That gave a big cost for the ISPs, but later the Chinese government can ask ISP to provide this kind of net log to find that. That's one thing. However, the most difficult part is if you find the bad guys, then what can you do? If you block this public IPv4 address, that okay, more than 1,000 customer cannot access all those.
Yeah, the impact is more than one device.
Yeah, right. And back to the second question you asked. Yes, there are lots of VPN providers or whatever, the clouds. So the bad guy can get into Amazon's VPN and do bad things. It's very difficult to trace back. And the trick the Chinese government is doing is you have to register the VPNs. Otherwise, that will block you. So that's the way. I don't like that idea, but that's their practice. The way is because people use VPN to bypass Great Firewall,
we cannot
bypass censorship. So that's why the Chinese government try. And the thing is because VPN is encrypted traffic, so they can know what's inside. Their way is if you are registered VPN, then like the Cisco in China, they register the VPN, so no problem. If there is a VPN and the government cannot identify, they will do randomly packet drop. So make your performance very bad. Then you cannot really use that. Okay, so that's their way.
Additional comment on your question. NET and the forensic. Year and a half ago, at the Apricot, Jeff Houston made a almost 1 hour keynote speech on that particular address. And you can find that in a video. And if you cannot find it, let me know. It's also in APSIG security or somewhere in those video address. That's really good. If you ever want to know NET and the forensic security issue, did a very good analysis. It's beautiful.
Okay. Thank you, Prof. Thank you. Okay. Thank you, Prof. Xing.
Thank you.
Thank you, Prof. Xing. Very nice presentation. I have two questions. One is very simple, basically. The Indonesian ISP, they are reluctant to move into IPv6 because they don't want to learn, basically. So what is China experience in forcing them to change into IPv6? That's the first question. The second question, I don't know, can I ask about E164? the phone number stuff? Because you are like focusing on IP-physics. Okay. So my question is more on the phone number, E164. We need phone number, especially for rural areas, because we are trying to build cellular network using our own base transceiver station, BTS. The problem is we cannot get any phone number allocation from the government. They are not really pro the villages. So right now we run the BTS using US phone number in Indonesian Papua, which is, so it's ridiculous. So we have been running enum server. Basically we steal the code area and then we run enum server. My question is it possible to coordinate or whatever phone number among other nations, because we are actually having difficulty to get phone number from Indonesian government. And then if there is so the first option, we are right now using US number, but if we can use other country number, it's fine, because US like $1 per number per month. So we need something lower. Okay, the second one is if we can run our own enum server, can we interconnect with other enum servers so we can make a call, that kind of stuff? So basically, the question for the enum. Thank you.
Oh, okay. So the easy question.
The first is the easy one.
Oh, okay. As mentioned earlier, the IPv6 trials are quite early in mainland China, and later it's very slow. But now recently, again, because the China is a single party government, Communist Party, that very strong. So the government, actually there is a interesting action plan, public available. As both the government, the Communist Party and the State Council jointly announced IPv6 plan. So that's very high level.
At that level, they are forcing.
Yeah, enforcing. And again, that's very technical. Okay, like for example, in this year, okay, 2018, all the provincial governments' website should support IPv6.
It's forced by the
by the government, and the top 50 enterprise or ISP, I mean the internet companies need to provide IPv6.
So they actually not forcing the ISP, they are forcing their offices.
And they check, because again, the strong government, if you cannot meet these requirements, the government will punish the ISP and punish the internet.
Okay.
So that's the Chinese way.
Okay.
I don't like it.
Well, I think we need to learn those things for Indonesia. Okay, the second question.
Okay,
I know this is
the second question, I believe, in technical point of view, numbers and the domain names and the IP address mapping, no problem. That's the governance issue. Because, for example, in China, actually we also try to sync for the WLAN devices to assign a number in the university, like EduRAM, those kind of things. However, in China, it's impossible because the telephone numbers controlled by them.
Do you aware anywhere in the world? Like
I remember when we tried Australia and New Zealand, they are trying academic e-numbers. So maybe, but that's like about 5 years.
Okay, I'll check.
Knowledge you can check Australia.
New Zealand,
really
that area. Okay.
Kind of.
Thank you very much. Thank you.
It's complementary talk.
Okay.
Just like last time. Okay, I'm going to comment both on this IPv4 and the DNS. first, back in the 1970s, we look into this issue of IPv4. Well, to be precise, IP. What shall I do in this IP? Because before them, we had an NCP, which is bad, and we had a consensus, so it didn't have any problem. So we had to come up with a new one, IP. Okay. Then this is a sort of almost apology as an engineer. Okay, we say like an engineer always overestimate in a short-term issue and underestimate in a long-term issue. Somehow that seems to be it's a nature of an engineer. If you think from now, okay, IPv4, 4 billion address, and everybody knows in the world we have 7 billion people. 7 is bigger than 4. So the 32-bit won't work, even if we give 1 each. And we couldn't see this long-term issue. And that's the reason why we are suffering. Like if we have only 1, not a 32-bit, if we have a 64-bit, then we don't have those issues, okay? And that's the engineer. So if you are the humanity or social science, don't trust the engineer, okay? I mean, when we design, you should get involved. Don't think we are the genius or the super something so that we do the right job. Never, okay? Always in the long term, social scientists, they are trained looking into the long term. Because they look into the 2,000 years ago, then naturally you look into the 2,000 years later. Engineer, no, we don't do that way. Yesterday and not tomorrow. That's all I have, okay? And so this is the problem. I was not directly responsible, but I could argue at that time. And of course, I believe in a 64-bit, but I didn't work hard enough, and many people didn't work. We had a, shall we do the 32-bit or 64-bit? We had those very severe argument. And we just made a, it's not $1 billion mistake, $100 billion mistake. Okay, next one, we made another mistake. Or you may say it could be a mistake. Do you know IP address you cannot own? IANA lends you. So that we are borrowing. So if we don't use properly, they can take it away, theoretically. Look into those internet governance. It's said that way. Then are we practicing? Okay, I don't say which company, okay? One company is a major company, okay? Has a 32 million address. Do you think that any company needs a 32 million IPv4 address? I mean, biggest company in the world, probably 1 million employee. Okay? And I really appreciate Stanford University. Stanford University also had a 16 million IP address. And back in about 20 years ago, they said, no, we don't need those 16 million. And probably in the world, we may need a lot of IPv4. So that we return. And they did return. And among those major universities in the USA, those are famous, about 5 or 6 universities, only Stanford did this job. Any other university, including my university, didn't do it. Okay? And that's the sort of, so that when you talk about the internet governance, okay, don't think everything is working well. In many areas, and this area seems to be those people who own, they don't want to touch. And if you want to hear, I'll tell you some awful story, but not now. or domain name. This is another those centrally control. Internet is distributed, we say, but the IP address and the DNS is a centrally control. This is a weak point of internet. And this is based on the Paul Mokapetris, the PhD thesis in the 1970s. So it's about 40, 50 years old, okay? And at that time he thought, probably, okay, let's have a 1,000 TLD. And each TLD server say like 1,000 users. And altogether we can serve 1 million. And why not? That's it, that was the idea. We didn't think about that those billion internet users. We thought about a million internet users. But again, this is an engineer, okay? In the long term, we always underestimate. And now, because of this DNS, we had IANA, and we barely made it to move the IANA away from the US government. And which I guess we appreciate. It's a very hairy move. We had it was 1 week late, this transition, we couldn't make it. We could not make it. So we made it within, because of about 4 days. Okay, and that one I can tell you if we want. Okay, now, what shall I do on this DNS? Like he said, like Facebook can handle the, now handling 2 or 3 million names, right? And their system can handle the 10 billion. As he said, then why do we need a domain name? You don't need a domain. Just a name is good enough. As the Facebook proved, then in the internet for next, Sarah, if you look into the next 100 years, are we going to use a domain name? That's something we have to think about. So that when you, in a school, in your country, okay, don't say that DNS is a perfect or this one lasts forever or anything, okay? It's a problem. Okay, fundamental, we have, I talk to the Paul every once in a while. There's a fundamental those flaw. Okay, just same as those IP address. So that again, don't trust the engineer. What is a fundamental flaw? Do you know who owns the domain name? Like you have a Gmail address or many of those addresses. Who owns it? Do you own? No. Either if it's a Gmail, then the Google owns. So they can, Google can change. Is that what we want? Well, since everybody is going to use the internet, why not when you're born, you have a ID, and which you use until you die. So the ownership, who should own? And if you own your own ID, then we don't have the centralized system anymore. And that's we are working on. Now, probably next time, I'm going to give those introduction. And if you want to see, it's a Veres one project. Do you know what kind of technology we use? Blockchain. Seems with the blockchain, not the one blockchain you use today. Blockchain is extremely lightweight. And we believe we could do it. Then there's several of those organizations working on this area, and I'm the one of them in the governing body, and we hope we'll do the experiment probably later this year, next year, and then we start deploying and using those blockchain technology, and it seems it works. And would you believe that Paul Mokapetris is also in this project member? He kind of, after doing the domain name, the 40 years, somehow he is convinced like each one of us should be the owner of his own identity. And then the blockchain very likely work, but we have to go through this experiment. And that one, probably I can give an introduction and probably a progress report next year, because we have to start it yet. And if you ever want to see this VERES, VERES 1 project.
Thank you. Any other questions?
One question from me. Hello. Okay, his question is, can you please throw some lights on the decentralized of names and numbers, and how can marginalized sections, especially people with different abilities of the society, benefit from this decentralization? Keeping in view the shortage of time, please reply in few lines.
Okay. I believe, like as Professor Kim Chang mentioned, currently the domain names is some kind of centralized. So distributed management actually is no problem. And the problem is how to make the uniqueness of the names. That's the major challenge. So yes. It seems the way to do that. Actually, I have a PhD student. We also try, like for domain names. Give you an example. They are authoritative, and they are resolvers. So they are distributed authoritative servers and the recursive server. So authoritative, you provide your names to people visit you, and the recursive is you find people, name and address mapping in the global internet. And our way is, how about to combine recursive and authoritative together? And each entity provide that with some kind of sign or CA or whatever blockchain things, maybe make things easier, and so you can do your own, but people, other domain name provider recognize you and trust you. So that's something. And what's the second question? All related to this? I didn't get the second one.
People with different, the society benefit from its decentralizations.
The society decentralization.
Now the question was, it is actually one question he makes in different ways. Okay.
I believe that in this fifth slide, for technology, I believe the currently most hopeful technique is blockchain to decentralize that. And for governance, I believe multi-stakeholder is the way to move forward. So how to combine multi-stakeholder with the blockchain technology, that will be something in the future direction. Also refer to Professor Kim Chang's thing, like you mentioned, engineers are short-sighted, and social science, long-term, yeah, right. Yes, I give you two examples. One is I talked to Wei Surf many years ago. I told him, the father of the internet, Wei Surf. So I asked him, if you redesign the TCP/IP, then what's you in mind? There are two things. One is 32 bits is not enough, so let's try to expand that. But I don't know, he didn't tell me it's 64 or whatever thing. I don't know. And the second more interesting thing is he said he will design TCP or UDP port numbers the same size as the address. So the address is the address, and the TCP or UDP port number are the identifiers. That's what he told me he will do this kind of thing. Definitely there are new problems for that, but that's, and the second thing, as I mentioned, we started IPv6 project quite early. And we are very proud of ourselves. So we built, okay, give you a brief history. We started CERNET, China Education Research Networking, back to 1994. Then we realized there is no enough IPv4 address for every student in China. In total, there are 320 million students in mainland China, the same size as the population in the United States. So we started IPv6 project back to 1998, joined the sixth boom. And later we built a dual stack network into year 2000 that's get funding from Natural Science Foundation of China. And then in the year 2004, we started CERNET 2, next generation CERNET. And that's the IPv6 only network. We realized dual stack is not good. Then we do actually IPv4 over IPv6. The people doing IPv6 over IPv4 is the sixth boom story. Then we realized, okay, in 1997, in IETF Dublin's meeting, I proposed our translation technology. That's we realized V4 and V6 need to talk. Then we get the standard of those kinds of things. And in the year 2011, that's the 100 years anniversary of Tsinghua University, my university. And by that time, we invited President Hu Jintao visit Tsinghua University, and we show how good of IPv6. And after about 10 minutes presentation, President Hu Jintao stopped us and asked if the IPv4 users outside Tsinghua University can access to your wonderful IPv6 content. So that's the question. That's actually really strike me because I'm an engineer. I realize V4 and V6 need to talk after about 10 years trials. But President Hu Jintao realized that in 10 minutes. It's not in. So he's an engineer. Yeah, he's an engineer, but not in networking. Yeah. So I really appreciate it. Sometimes we engineers need to listen to the politicians. They have a long sight. That's a real example.
Okay, then I give you some clarification on the mental exercise. Okay. Back in the 1970s, we had a choice, as I said. Shall we do the 32-bit or 64-bit? It was almost a fight by several of those parties, and I don't want to get into that part. Okay, here what I want to say is that then we decide to the 32-bit. Okay, that's the IPv4. That's a history. Either you like it or not, that's what we have. So what I said, like engineers tend to underestimate in the long term. Okay, now come to the mental exercise. Is 64-bit is good enough? Do you know how big is a 64-bit? If you do the 64-bit, 32-bit give a 4 billion. Okay, so the 64-bit you can is roughly speaking, each one of us can have more than 1 billion address. Okay, mental exercise, is it good enough? Because this is one problem we are going to use the next 100 years. So the 100 years from now, do we regret having 1 billion address per person? And of course you say, oh, that's more than plenty. But we said the same thing in the 1970s. And let's give a credit to the Bint. Okay, Bint of course involved in a 32-bit or the 64-bit. He was not in a position to decide anything, okay? But he's one person who involved. Then recently, about in the last about 10 years or so, like we had a discussion. Then somehow he think 64-bit may not be good enough. So I guess 128-bit may be the correct decision. And think about, if you can have a 1 billion or more address per person, do you really need much more? And of course, like if you live 100 more years, you can find it out. But this is a kind of things we have to make a decision. And when you make this kind of decision, from now on, engineer alone to make a decision is wrong. We have the social scientists together because since sometimes they have a much better those insight in the longer term. So many of those issues, we are sort of asking a social scientists, or even those humanity, people working in art, to get involved. And communication is very difficult because we use a different language. And that's the way. So think about 64-bit can give you more than 1 billion IP address per person. Then why can you think that's not good enough? Okay.
Thank you for the presentation. And you, like I said several times, you don't like how Chinese government have been doing, the top-down control. So I'm wondering how you deal with that kind of a political situation as an engineer. So in terms of developing technology, and then you also by developing technology, you're also shaping the world. So is there your a stance as an engineer to fight back the central government control through the developing engineers like a blockchain you're thinking of?
Okay, that's a tough question. Yeah. Okay, I believe based on my experience, if you are a follower, the Chinese way is good. Because you see US is doing those kind of things, you just follow that, Huawei also can see. However, the real innovation is unplanned. That means the new innovation should be bottom up, not top down. Top down can be a good model for follower, but not for the leader. Leader, you need to have a freedom of research or those kind of things, because all things are planned. That's basically the thing. And the blockchain actually is some way to move forward. That's good. Yeah, I can also give you a thing quite interesting. The blockchain, right? And in mainland China, because the propaganda is controlled, if people post something the government does not like, then the government will force the ICP to delete that. So that's the way it works. However, some smart people use blockchain to sign that announcement, and it cannot be deleted and is still available. That makes the governmental control very tough. So actually the Chinese government really promote blockchain technology, but they does not realize there is a side effect for this that will destroy the deleting of the posts. I don't know what's the way to do that. Maybe there are some new ways, but actually decentralization in nature is against the government to control whatever the Chinese government or US government. That's really something. I can give you another example in IETF. In the year, Snowden, right? So when Snowden first post their things in Southern China Post in Hong Kong, then Snowden said, the NSA get hacked into Tsinghua University, and that's the center of CERNET. So those kind of things. And after that news release, I attend IETF. I try to ask U.S. engineers or colleagues, what do you think about Snowden? Nobody answered. It seems like the Chinese engineers love China. U.S. engineers love United States, so that's the country conflict. However, after that, Snowden also said there are backdoors in Android, iOS, or even BlackBerry. And then the following IETF, there is a plenary. In the morning, actually, I never see IETF plenary in the morning session. And in that session, actually, there is a big discussion in IETF, discuss Snowden effect, because the engineers realize people or engineers are good guys. All the government, whatever US or China, are bad guys. We need to protect ourselves. So that's thing. And
Don't you think that's correct?
I don't know. I don't know, but that's quite interesting. That's why we need multi-stakeholders, so people need to talk and make the balance. There are 5 questions asked in IETF. The first is large-scale surveillance. Is that an attack, network attack? So the answer is, it is attacked, whatever the monitoring of. And the second, if that's attacked, then should IETF take actions? And also very strong yes, said yes, we need to do that. And the third is, should we introduce encryption, even without authentication? So, and the answer also quite strong, yes. And the fourth question is quite controversial. The question is, should we introduce end-to-end encryption if there's a middle box in between? What's the meaning of middle box? NSA's tapping is middle box, and the Chinese Great Firewall is a middle box, including the enterprise firewalls or whatever are the middle box. And the answer is some kind of controversial, but more yes than no. And I was in the IAB on the stage, and I said, wait a minute. For example, I didn't mention China precisely, but I said some country has some kind of national policies. If it's a clear text and the content is not sensitive, the government will let the packet go through. If it's sensitive, then block. However, if end-to-end encryption, the government cannot monitor what's good or bad. The only thing they can do is block that. So if that's the case, that's the fragmentation of the internet. Some people reply me, and after the meeting told me, yeah, point out something important. And the fifth question is, should IETF develop all the security protocols in companion with the secure protocols? And the answer is yes. Well, whatever. So the IETF final decision is, in the next 5 years, probably will push HTTPS. And probably 50% or maybe 90% of the website will use HTTPS rather than HTTP. And if the Chinese government or whatever other governments still use the current block method, then that will be the fragmentation of the internet. That's really scary. That's some story, real story. So, thank you very much.